Okay, guys, in this chapter, we are going to be talking about the periodic properties, which is referred to as periodicity, um, basically categorizing all the elements. Make sure you have your periodic table out. I suggest having one printed that you can write all over, color code, that kind of thing. We're also going to be talking about electron configuration. This also will probably be split up into two parts. Haven't decided yet. All right, so let's go. All right, so periodic law just basically states that elements in certain columns of the periodic table are going to have repeating predictable patterns. Say for the transition metals, we'll get to that. But repeating patterns means it's going to do similar things as far as how it reacts, how it bonds with another element as something else within its own column. We also talk about these in terms of families. So, for example, you are not your brother, you are not your sister, you are not your mother or father. But you might think, okay, well, we have a lot of similar properties. We might have the same kind of inflection in our voice, the same kind of gait when we walk, but we're clearly different people. Elements are going to behave the same way. So some properties are trends, some properties are hard and fast rules, and with everything chemistry, there's an exception to every single rule. If you look here, it's comparing boron to aluminum, gallium to indium. Now, if you look at your periodic table, you will see that boron, just like that's shown here, is above aluminum, which is above gallium, which is above indium. Now, what you'll notice is there's a trend with the radius. For example, the atomic radii. We're going from 85 to 143 to 135 to 166. The general trend is that it increases as we go down the column. Gallium, of course, is an exception because 143 is a larger number than 135. We don't need to worry about, as far as atomic radii just yet, why it's an exception. Okay, so I'm not going to read this to you, but the whole idea is that 19th century, which is 1800s, remember, no running water, no indoor plumbing, no electricity. Experimentally, they've been able to discern that certain groups of elements that we discovered, that we had discovered to this point, had certain patterns. They had properties. They were similar. They behaved similarly. Now, I want to just kind of put this into perspective a little bit. Again, you don't need to know history dates. I don't even know the exact dates. I just know ballparks. Way back, thousands of years ago, we already know that humans on Earth had discovered things like gold, silver, platinum. I mean, heck, look at the royal families of Europe all the way back thousands of years, 2,000 years. So there were some things that we already knew and we had already discovered. Later, things would always be discovered. At the point in time we're talking about, we maybe had two handfuls of identifiable elements that humans had discovered. Okay, so we get these reoccurring, repeating patterns, similar properties, similar behavior, similar trend in things like density, atomic radii, metallic character, all these kinds of things. Mendeleev is the grandfather of our current modern day periodic table and the way it's all formatted. All right. So originally, he arranged the elements that we knew of in order of increasing mass. Okay. But then he realized that's just not good enough. So at this point, every element you see there, we knew existed. And he just put them in order of increasing mass. he's going to find very quickly that that is not, well, I don't think he even knew it, but later scientists decided that's not the best way to organize these elements. So Mendeleev's periodic table organization, um, it's in it's in like a table format. Let me see if there's a picture here. No, his is not there. At any rate, it was kind of a table. And so, with the few elements that we had already discovered, he put them in order of increasing mass, and then also experimentally found that some elements, um, behaved similarly than others, and then created the rows and the columns to get kind of this table. Think of like an Excel spreadsheet table, right? Okay, so the problem is there were missing pieces. There were missing pieces to the puzzle. There were missing, just based on the properties that he had experimentally figured out. He said, all right, we're missing something. There's something we haven't discovered yet. So he would have not discovered these, but he knew that there was things that existed on the earth that were not discovered yet. How do we know this? We're going to look at specifically gallium and germanium. Okay, so if you look at gallium, again, based from a few slides back, it's just below aluminum. So Mendeleev's first prediction was Eka aluminum, okay, meaning a variation of aluminum. And what we know it today to be is gallium. He looked at properties of aluminum and properties of indium and realized very quickly something's missing in the middle. And so he predicted this unknown element to him of the atomic mass, the melting point, the density, the formula of oxide, meaning how will it bond with an oxygen, the formula of chloride, again, meaning in what ratio will it bond with the chloride ion. And look at these numbers. Look at how accurate they are. That's what he predicted. That's the actual density of gallium. Prediction, actual atomic mass unit. Melting point, low. Melting point, low. Now, let me put into perspective 29.8 degrees Celsius. The freezing point for water is 0 degrees Celsius. The boiling point for water is 100 degrees Celsius. In most air-conditioned rooms and buildings and homes, your average air-conditioned temperature is roughly somewhere between 27 and 29 degrees Celsius. So what that means is the second you put gallium in your hand, it's going to start to melt. Formula of oxide, predicted, exact. Predicted, exact. The same thing happened with germanium, which if you again look on your periodic table, you're going to see it's exactly to the right of gallium. Eka silicon. Why Eka silicon? Because it's a variation of silicon, which is literally right above it on the periodic table. These predictions were very true. He was able to predict with such accuracy because of these repeating predictable patterns. So, on the periodic table, rows, left to right, are referred to as periods. Columns, top to bottom, are referred to as groups or families. So this is a group or family. That is a period. So this is an important thing to note right here. Mendeleev's periodic law predicts patterns, but it never explains why these patterns exist. We have groupings on the periodic table: metals, nonmetals, and metalloids. And some of these different groupings are going to have different titles to kind of categorize them. So we can divide the periodic table up into metals, nonmetals, and metalloids. We can also divide the periodic table into main group elements and transitional elements, okay? The main group or representative they are predictable. They have certain properties. They are repeating. They have very similar behaviors when it comes to chemical reactions and how they bond with other elements. The only thing regular and predictable about transitional metals is that they are not regular and predictable. For the purposes of this course, when we get into working with the transitional metals, I'm going to have to either tell you what that kind of transitional metal is, or I have to give you enough information to figure out. I don't ever expect you to just know, oh, this will become, iron will be a +2 ion here or a +3 ion there. Why? I will give you the information or tell you what it is. So here's our periodic table. We're going to talk about a lot of things on here. All of those are your metals. Okay, oh, I kind of went too far with my red line. I'm sorry. Change colors. Now, your stair step I'll get to the rest of it. Hang on. This is your stair step, and these are your metalloids. Okay, or semimetals. You've probably heard that name before. All right. All the rest are your nonmetals. Okay. Now let's talk about this group down here. These are also metals. Okay. So we have 3 sections of the periodic table where we go from left to right, decreasing metallic character. So as we go up the periodic table and to the right, we have decreasing metallic character. Now, this should make sense considering that all of the metals are on the left. Then we get these semimetals or metalloids. And the semimetals and metalloids, they will behave like a metal or a non-metal depending on what they're reacted with, what they're bonded to, etc. Okay? And then the non-metals are all the way on the right. So it should make sense that we have decreasing metallic character as you go up into the right of the periodic table. Now, generically, outside of that, we can say this group and this group are our main group elements or representative elements. We can't just call them metals flat out because some of them are nonmetals. These are the ones that are repeating patterns and predictable. The transitional elements are here. Oh, sorry. The blue. And these are your inner transitional. Okay. Now, let's talk about the inner real quick. If you see, there's a line here, and it spits out to the arrow that goes here. Now, if you can imagine squeezing this together and fitting it right here, that's where it would go. How do I know that? 57, 58, 59, all the way down to 71, bam, 72. 89, 90, 91, all the way down to 103, 104. Okay, so that's where it fits into. Now let's talk about some categories. This is out of order. Okay, we're just going to talk about the categories. All right, this first family are the alkali metals. This next one is they are the alkaline earth metals. Okay, we have our transitionals and our intertransitionals. We have our halogens and we have our noble gases. There are no other categories like that with any of the other columns. Bromine and mercury are the only two elements on the periodic table that occur naturally in nature as a liquid. The metals occur naturally in nature as a solid, and the non-metals, except for bromine, occur naturally in nature as a liquid. I just said that backwards. As a gas, except for bromine, which occurs as a liquid. Now, I don't want you to get confused about one thing. The one thing I don't want you to get confused about is hydrogen. Hydrogen is a non-metal. It occurs naturally in nature as a gas. The reason it's over here in group 1 is because of its behavior. It behaves like these other group 1 metals. Okay? So don't think, oh, hydrogen's a metal. It is not. We just kind of throw it over there on this periodic table because it behaves like that. Sometimes on some periodic tables, you'll see hydrogen over here in the middle, just so you know that it's a non-metal, but it behaves like the group 1 metals. The last thing I want to talk about on this are the diatoms. Diatoms are elements that are non-metals that naturally occur in nature in their doubled up format. What do I mean? I mean they'll naturally occur in nature as a hydrogen bonded to a hydrogen, for example, and we call that H2. There are 7 of them, and they make the shape of a 7 on the periodic table. Here they are. So, N2, O2, F2, Cl2, Br2, I2, and don't forget hydrogen, H2. 7 diatoms on the periodic table. They're the only ones that naturally occur in nature in that format. So N2 would be a nitrogen bonded to a nitrogen, oxygen bonded to an oxygen, etc., etc. Okay. Electron configuration means that we are going to be talking about how electrons fill around the nucleus. Okay? How they fill and where they are two different but the same things. So let's just talk, let's talk about spin first before I get into my little picture. So electrons occur in pairs, and because they occur in pairs, one is going to spin upwards, one is going to spin downwards. They're going to spin opposite of each other. And we use a half arrow to represent one electron in a pair. So where's my picture? We'll get back to Z effect. All right, so let's just talk about electron configuration. So down here's my nucleus, and this is where the lowest energy is. Way out here is my highest energy, and electrons will always fill from lowest to highest energy around the nucleus. Okay, so each one of my orbits here represent a fixed main energy level. So this is main energy level 1. What is happening? There we go. So n equals 1. This is n equals 2. N equals 3. N equals 4. And n equals 5. Okay? Within each fixed main energy levels, we have the sublevels that we talked about last time. So you have the S sublevel. S can hold up to 2 electrons. You have the SP. Note I drew 3 lines because P can hold 6 electrons, which means 3 pair. Okay, I have n equals 3, so guess what? S, P, D. D can hold up to 10 electrons, therefore 5 pair and 5 lines, because remember, each line is going to represent one of the orbital pathways that it takes. 4, S. Oh, I drew too many. Oops, sorry. Getting ahead of myself. P, D, and F. I'm running out of room. 1, 2, 3, 4, 5, 6, 7. F can hold up to 14 electrons, which is 7 pair. Now, pull out your periodic table, and we are going to look first at, we'll look at oxygen, okay? Oxygen has a total of 8 electrons. I know that because its atomic number is 8, and the atomic number is the number of electrons in a neutral, non-charged oxygen. Okay, so these electrons are going to fill around the nucleus from lowest energy to highest energy, so closest to the nucleus, and then go further out. And we're literally just going to go in order. N equals 1, N equals 2, N equals 3, N equals 4, and going through all of these. But there are some exceptions, and we're going to get to those exceptions. Okay, so first things first. 2 electrons can fill S. So there's 2 of those 8 electrons and where they're going to be. I'm left with 6 to deal with. Going to bump up to S. Now watch how I fill this next one out. I'm going to do 1, 2, 3, and then go back and double up. Okay? I'm going back and doubling up because it is more stable to have 2 half-filled orbitals and 1 full orbital as opposed to 2 full orbitals and an empty. Okay? So that's my 4, and I'm done. So the electron configuration, this is where all the electrons are. So when we write this out, we're going to say the electron configuration for oxygen is 1s2, 2s2, 2p4. The coefficient is the main energy level, the letter is the sublevel, and the superscript is the number of electrons in that orbital. So let's do another one. I'm going to do now, we'll do magnesium. No. Yeah, we'll do magnesium. Okay. Magnesium, by looking on the periodic table, I see that it has 12 electrons. It has 12 electrons because in a neutral magnesium, the atomic number is the number of protons and electrons. That is not true of a charged element, but we'll get to the charged ones in a minute. So I'm going to do the same thing. 1, 2, there are my first two. 1, 2. 1, 2, 3, double up. 4, 5, 6. 1, 2. And now I'm done. So its electron configuration is 1s2, 2s2, 2p6, 3s2. Okay? Now we're going to do one more. And then I'm going to show you the trick. Oops, forgot to erase those. Actually, you know what? I'm going to keep those up. No, we're not doing aluminum. We're going to do gallium. Sorry. We're going to do gallium. Gallium has 31 electrons. So just like magnesium, it will fill up to this point. So that's a total of 12 that we've already used. So I got 19 electrons left to place. So 1, 2, 3, 4, 5, 6. $13 left. Now, you might just say, okay, now we're going over to D, correct? Not correct. That seems logical, but we're actually going to go up to S first, go back to D, then go up to P. Why in the world would we do that? Well, remember I told you the rule was that the electrons fill from lowest to highest energy. So if we're going to fill 4s first, that should tell you 4s has a lower energy level than 3d. Okay? So we're going to come up and say 1, 2. So we go up there. That's step 1. Then we're going to go back to 3d. Let's maintain our math here. 1, 2, 3, 4, 5. Double up. 6, 7, 8, 9, 10. So that's step 2. Then we're going to go back up to P. 1. Okay, so its electron configuration, written in order of fill, will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Okay? Again, the coefficient tells us what main energy level, the letter tells us the sublevel, and the superscript tells us how many electrons are present. Okay, now I'm going to show you the trick. We're going to divide this periodic table up into S, P, D, and F sections. Okay? So if you could just imagine in your head, all of these we're going to call S, all of these we're going to call P, all of these we're going to call D, all of these down here we're going to call F. So, 1, 2, no, I did that wrong. Hold on, stop. No, I didn't. Okay, those are if you look on your periodic table, you will see those numbers are on the left-hand side, and I also kind of like to write them on the right-hand side, just so I can keep track. It's easier when I'm looking and I'm going to do about what I'm going to do. Okay, now we're going to change up the numbers. So as we look left to right on the periodic table, 4 is S, D is going to drop down to 3, 5 is S, D is going to drop down to 4, 6 is S, D is going to drop down to 5, 7 is S, D is going to drop down to 6. Now, one more caveat. F, 6 is S, 5 is D, F is going to drop down to 4, 7 is S, 6 is D, F is going to drop down to the number 5. Okay, now, what we're going to do is we're going to read this periodic table left to right, top to bottom. And then we are going to pretend each box of the periodic table represents one electron in whatever element we're trying to find the electron configuration for. So I'm going to go back to oxygen because that was the first one we did. And we're going to try to find the electron configuration. So what I'm going to do is I'm going to say, okay, my stopping point is oxygen. So we are doing oxygen. Now, I'm going to read the periodic table top to bottom, left to right, just like I read a book. And I'm going to pretend each box represents one electron up to and including oxygen. So I have 1s2, 2s2, 2p4. Okay, that's the periodic trick with electron configuration. Let's do now magnesium. Okay, magnesium, here it is. 1s2, 2s2, 2p6, 3s2. And that's the electron configuration. Last one, we're going to do germanium again. So germanium has the same, not germanium, gallium, sorry, has the same electron configuration as magnesium, up to and including 3s2, so I'm just going to recopy it. Okay, so 1s2, 2s2, 2p6, 3s2, now we're going to hop over here, 3p6, 4s2, nope, we drop down one number, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 4p1. Okay, and that's it. That's the trick for electron configuration. I'm going to stop here with this particular video. The next part will cover valence electrons, core electrons, ions, electron configuration for ions, and the exceptions to these rules.